Hello, my name is Rafael Noga. I'm with University of Valladolid and I'll present the NMPC for Superfluid Helium Cryogenics that has been developed together with Professor Otska from Kyoto University, Professor De Prada from University of Valladolid, Dr. Blanco and Dr. Casas from the European Organization for Nuclear Research. This is a proof-of-concept non-linear model predictive controller for the Superfluid Helium Cryogenic Circuit at the Large Hadron Collider, and it's based on a relatively complex model, and we've developed two configurations corresponding to different control strategies and manipulated variables. NMPC number 1 manipulating two control valves that has been experimentally tested at the LHC, and the NMPC number 2 manipulating two control valves and 12 electric heaters that has been only tested in simulations. The superfluid helium cryogenic circuit contains the superconducting magnets of the LHC at its operational temperature of -271 Celsius. The temperature dynamics is extremely complex and nonlinear, and thus the interest to develop the NMPC. So the model that we use in the NMPC is the first principle distributed parameters models, and it has been developed following a specific modeling approach that led to very low computing cost of simulation of the model simulation. The hybrid Luenberger moving horizon estimator is used to provide the information about the current state of the system, and two NMPC formulations have been developed: NMPC 1 with 6 decision variables and NMPC 2 with 18 decision variables. The nonlinear optimization problems have been formulated in a simplified manner as box inequality constraint nonlinear programming problems, where all the non-box constraints are only approximatively implemented through the cost functional. Then simple numerical solver has been used to solve those nonlinear optimization problems. The model and the optimizations have been implemented in C and allowed us to test the system at the LHC and in simulations. The results are visible here. Actually, we are simulating the heat loads here. The red dashed line corresponds to the heat loads to the system, and those heat loads here, the pattern corresponds to the nominal LHC operation. In this case, the varying heat loads causes the perturbations the maximal temperature. That's nicely stabilized by the NMPC number 1 in this case, 10 times faster than the PI controller is able to do it. In the second test, the same NMPC 1 stabilized temperature in the presence of much higher heat loads, or let's say those initial standby heat loads, and this causes the temperature dynamics of the system to be very different. However, the closed loop dynamics is almost identical as in the previous case. Here we see the NMPC number 2, where we manipulate not only the control valves but also the electric heaters, and what we see here is that the electric heaters can very fast compensate for the increasing heat loss, and thus significantly improving the closed loop response. What we also see is very low computing time for the NMPC update. The black dashed line here corresponds to the 7 seconds of CPU time for the NMPC number 1. Here we see 30 seconds constant for the NMPC number 2 and around 1 second for the moving horizon state estimator. We also see a very nice convergence of the first order optimality conditions for the NMPC number 2 and number 1, number 2, and the visibly worse convergence for the moving horizon state estimator. However, this worse convergence has no visible effect on the performance of the estimator. Finally, the NMPC has demonstrated excellent robust closed-loop performance and real-time feasibility of an online NMPC using complex first principles model. Thank you very much.